Welcome to episode 9 of the SES course. In this episode, we will learn how to develop DApps using Solidity smart contracts on SES. We'll cover setting up wallet accounts, address conversion between Substrate and EVM, and transferring funds between the two. Additionally, we'll deploy a sample Flipper contract on SES testnet and explore the proof of existence smart contract sample code with a front end to interact with the smart contract. This will provide a better understanding of smart contract structure, allowing you to write your own smart contracts. Why choose a Solidity smart contract? Let's explore why Solidity smart contracts are a preferred choice for developers and why it is advantageous for SES to support them. Extensive developer base. Solidity is the most widely used programming language for smart contracts, boasting a large and active developer community. This broad adoption means that many developers are already familiar with Solidity, making it an accessible entry point into blockchain development. Proven track record. Solidity has a proven track record, having been the foundation for numerous successful projects and applications. As a mature and battle-tested language, it offers reliability and stability, essential qualities for developing secure and robust decentralized applications or DApps. Rich ecosystem and tooling. Developers working with Solidity benefit from a rich ecosystem of development tools, libraries, and frameworks. This ecosystem includes everything from development environments and testing tools to deployment frameworks, making the development process more efficient and streamlined. Strong community support. The Solidity community is vibrant and continuously contributing to the language's improvement. This strong community support ensures that developers can find help and resources quickly, whether through forums, online tutorials, or collaborative platforms. The active community also means frequent updates and enhancements to the language and its tools. Interoperability with EVM chains. One of the key advantages of Solidity is its compatibility with the EVM Ethereum virtual machine. This interoperability allows Solidity smart contracts to be deployed on any blockchain that supports EVM, providing developers with the flexibility to build applications that can interact across multiple blockchain platforms. Comprehensive documentation. Solidity comes with extensive and detailed documentation, making it easier for developers to learn and implement. The availability of comprehensive resources aids in understanding the language's nuances, best practices, and advanced features, helping both new and experienced developers to build efficient and secure smart contracts. SES support for Solidity. By supporting Solidity smart contracts, SES lowers the barriers for developers familiar with Solidity to start building on the SES platform. This not only attracts a larger pool of developers, but also leverages the extensive resources, tools, and community support that Solidity offers. The integration of Solidity within the SES ecosystem can lead to a richer, more diverse range of applications and innovations, fostering a dynamic and thriving development environment. Common used libraries. Let's take a look at some commonly used libraries in decentralized application development, highlighting their features and how they can be utilized. Polkadot SDK. First of all, let's talk about the Polkadot SDK. The Polkadot SDK is an umbrella project encompassing 3 sub-projects: Substrate, Cumulus, and Polkadot. These projects collectively enable developers to build robust and scalable blockchains. SES, the platform we're focusing on, is built on top of the Substrate framework. Substrate is a modular framework that allows you to create purpose-built blockchains by composing custom or pre-built components. Cumulus enables Substrate-based blockchains to connect to the Polkadot network as parachains, leveraging shared security and interoperability. Polkadot, the main network, provides a scalable and interoperable ecosystem for all connected parachains. You can explore more about these projects through their respective documentations and repositories. Polkadot.js API. The second library is the Polkadot.js API. This is a set of JavaScript/TypeScript libraries designed to interact with the Substrate-based blockchains. It includes utilities, cryptographic functions, and hash functions, making it a comprehensive tool for developers working within the Polkadot ecosystem. With Polkadot.js API, you can connect to Substrate-based chains, perform cryptographic operations, execute transactions, and read on-chain data. Ethers.js. The third library is Ethers.js. This is a JavaScript library used to interact with Ethereum virtual machine smart contracts. Developers can use Ether.js to retrieve smart contract instances, read on-chain variables, and make transaction calls. Key functionalities include connecting to the Ethereum network, interacting with smart contracts, and handling wallet operations and transactions. WAGMI. The fourth library is called WAGMI. WAGMI is a React hook library designed to interact with EVM smart contracts. If you are building a React front-end to interact with Solidity smart contracts, WAGMI provides essential functions such as connecting or logging in with the user wallet, getting the smart contract instance on the hook, and managing interaction flow. WAGMI simplifies tasks like wallet connection and authentication, fetching and interacting with smart contract data, managing transaction states and responses. These libraries collectively offer powerful tools for DApp development, each catering to different aspects of blockchain interaction. By leveraging these libraries, developers can build, interact with, and manage blockchain applications, ensuring robust and scalable solutions in the decentralized ecosystem. Substrate EVM address conversion. Now we're going to discuss one of the most important topics for Solidity development on SES. Firstly, it's worth noting that on Substrate, the address is in SS58 format, which means it is in base 58 encoding. As computer programmers, we typically work with base 10 decimal numbers or base 16 hexadecimal numbers. Base 16 is represented by the numbers 0 to 9 and the letters A to F. On the other hand, base 58 is like representing numbers from 0 to 57 using a single character. Let's open the base 58 mapping table URL and scroll down to the base 58 mapping table. As you can see on this table, base 58 skips characters that could be misleading to readers. For example, it skips 0 because it looks similar to the uppercase O, and it skips the lowercase l because it looks similar to number 1. It also skips the uppercase I for similar reasons. So this encoding uses a specific set of 58 characters, and we see the same method is used in Bitcoin address. Here is a SES address, CXJH. This is just an example shown here base 58 format. We can decode it into hexadecimal using a base 58 encoder/decoder. Copy this address, paste it into the decoder, and decode it to get a hexadecimal output. This output will include public keys for the address, which is the highlighted part of the decoded hexadecimal string. We can also inspect from this the command line if you have a SES node binary running, by running the command key inspect, followed by the SS58 address. You can see the detailed information. This includes the public key, network prefix, and checksum. The network prefix uniquely identifies each network within the substrate ecosystem. For the SES testnet, the network prefix is 11330, which is 0x50AC. The prefix, public key, and checksum are concatenated and encoded into the SS58 address. The hexadecimal network prefix may undergo byte shifting for accurate representation. Substrate and EVM address generation. Let's examine how substrate and EVM addresses are created. For substrate addresses, the process involves taking the private key, passing it through an elliptic curve function called SECP256K1, adding the network prefix and checksum to the output, and finally base 58 encoding it using the base 58 encoder to obtain the substrate SS58 address. On the other hand, the EVM address is also known as H160 format address, which is 20 bytes or 40 characters long. Similar to the substrate process, the first step in generating the EVM address is to take the private key and pass it through the specific elliptic curve function SECP256K1. However, in the EVM process, the output of the algorithm is then passed into another hashing algorithm, KECCAK256. The final EVM address is derived from taking the last 20 bytes from the hash digest output of this function. Substrate and EVM address conversion. Now that we understand how the addresses are generated, we need two sets of accounts to transfer funds between substrate and EVM addresses. First, we will create a substrate signing account and an EVM mapped account, which we will call account set 1. The conversion can be done using the address conversion tool. Similarly, we'll create another account set and call it account set 2. It's important to note that we cannot directly transfer tokens from a substrate account and account set 1 to an EVM account and account set 2. To do so, you will need to have mapped account address of EVM and substrate or vice versa. Once you have the mapped accounts, when you transfer funds from your substrate signing account 1 to substrate mapped account 2, the funds will automatically be available in the EVM signing account 3, which is mapped with substrate mapped account 2. On the other hand, if you transfer funds from your EVM signing account 3 to EVM mapped account 4, which is mapped from your substrate signing account, the funds will be available in your EVM mapped account address. To get it back to your substrate signing account, there is an additional step of withdrawing the funds from the smart contract, which involves sending a withdrawal transaction. In the next section, I'll demonstrate the entire process of transferring tokens from the signing account to a mapped account and back, ensuring you understand the complete workflow of managing balances between these accounts on SES.